It's a pleasure to welcome our next speaker, Olivier de Weck from Massachusetts Institute of Technology, who is indeed going to tell us how to get to Mars cheaper via the moon. Is that right?
That's right.
Okay, Olivier, and can we dim the lights a little bit, please?
Thank you, Ian. It's a great, so two quick comments. It's a great pleasure and honor to be here. A wonderful city in London and a very traditional and very well-respected institution. And the second is, I don't remember ever giving a talk that was this well sequenced right after Dr. Spudis, because I'm going to provide a very similar message to you, but using a somewhat different approach, but coming up with very, very similar conclusions. And so my message to you is essentially beyond this detailed result here that I want to share, which is that going to Mars via the moon, if you do it the right way, can save you up to 68% of launch mass instead of just going directly to Mars. That it's time to think about this as a supply chain, as an interplanetary supply chain and a network perspective. That's really my main message. So we heard about Apollo. It was very successful, clearly, but nothing was left behind for any of the other missions. The paradigm in Apollo was what we call carry-along, or think about it as the backpack model. You leave with a big backpack, you consume things, and you come back with almost nothing. And then you can flip that, and that's the current paradigm we're in with the International Space Station. This is a resupply-based paradigm, one node in space, and we now have 5 different resupply locations from Earth. And the future, we know, is going to be much more complex. The International Space Station will continue to be operated at least until 2024. And then the question is Moon, Mars, and beyond. And so this brings up many interesting questions, again, from a network or logistics perspective. What's the right mix of carry-along, resupply, and pre-positioning for future missions beyond low Earth orbit? What are the demand drivers in terms of exploration, both with humans, with robots, and for astronomy as well? And then what are the most critical technologies, and what performance level or maturity level do these technologies need to meet to really be useful? And that's also a question I'd like to address. So to give a little bit of background about our work in this area, it goes back about 12 years. In 2004, we wrote a proposal called Interplanetary Supply Chain Management. And I think the expectation we had for funding was like 1%. And we were very surprised that it got funded. This was at the very beginning of the Constellation program. And since then, we've graduated about 25 students in this area. We've also developed a software package called SpaceNet that allows you to essentially model these interplanetary supply chains, not just for individual missions, but for entire campaigns. This is open source. Anybody can download it. Anybody can use it. It has user manuals, examples, and so forth. Let me share with you some of the scenarios that we've modeled in SpaceNet. Of course, the ISS resupply. We modeled the 2000 to 2008 resupply sequence when we still were operating the shuttle. That was a total of 78 flights. We also modeled Mars campaigns with robotic precursors. And the idea would be you send robotic precursors to the 3 top sites for human landings, and then you follow up with a human landing. Of course, the lunar outpost near Shackleton Crater that we've already heard about. This is the most ambitious one. This is a nomadic lunar exploration scenario where each team basically carries their ascent stage with them, explores the moon for a stretch, leaves, and then the next team starts where the last team left. And then after a sequence of missions, you essentially traverse the entire front part of the moon. This is, of course, risky, but quite doable. So what have we learned in modeling all these campaigns with SpaceNet? It's complex. So ISS resupply involves 9 nodes, 13 edges. These edges, by the way, have very detailed trajectories and astrodynamics behind them. They're shown as simple lines here, but there's a lot of detail. Like I said, 78 missions, 271 events, and then you can see the mission durations. You start going from hundreds of days up to a full Mars exploration campaign is 7,000 days. So that's over 20 years. And so these campaigns involve hundreds of events over thousands of days. And bringing everything from Earth is not sustainable. We've already heard this today, and I'm sure we'll hear it again. So we need to start thinking about it differently. We need to think about this problem as a supply chain network in space. And this is what we think this network looks like. So we have definitely the Earth and Moon. This is our cislunar system. The color of the nodes are meaningful. So the Earth-based nodes, our main launch sites, are in blue. Lunar nodes, but also the moons, of course, of Mars, Deimos and Phobos, are in green. We can potentially get resources here, metal oxides, oxygen, hydrogen, and so forth. We'll talk about it some more. Mars, we do see Mars as a destination, and the moon, of course, as well. And very interestingly, the Lagrangian nodes, which have many interesting features, such as halo orbits, and very interesting gravitational property, great places potentially to put depots. Now, the question we ask here is, how do we optimally select a logistics network? The combinations there's millions of possibilities here. So how do we know which ones are the most attractive ones? That's really what I want to get to. And of course, one thing you need to know about is where the resources are. Dr. Spudis has already talked about this in great detail. We agree, especially the south polar region of the moon looks to be quite interesting for water ice. So here's essentially the approach that we take. It's a graph-theoretic approach using linear programming and mixed integer linear programming. So we do not presuppose which of these nodes are really the most interesting, which of the trajectories should we use. We let the optimizer tell us what is the optimal network. And so we set up the problem, we set some boundary conditions, some technological assumptions, and then the optimizer automatically explores millions of opportunities and gives us answers. And I want to share some of these answers with you. Before I do that, let me tell you a little bit about the formulation. So a few things were necessary to generalize this from traditional commodity flow analyses as we see them in terrestrial problems. So first of all, multi-commodity implies that we have a vector of commodities, the vehicles, the crew, the supplies, scientific equipment, spares. All these things form a large vector. And in this work, our vector is has 30 different entries. And the flows, we model the outflows and the inflows into the nodes separately. The reason for this is because you can have losses or gains along the way. For example, the crew will consume resources on the way to the moon or Mars. So, and you're converting also commodities from one type to another. So this commodity conversion is a key aspect. We also have self loops. So essentially a resource production facility or a fuel depot, you model this as a self loop at the same node. And we also have, if we look at these constraints here, really three types of constraints. Mass balance constraints that enforce essentially conservation of mass and equilibrium. We have the flow transformation constraints, which allow you to transform the commodities from one type to another. And then we have the third type are these flow concurrency constraints. So if you want flow of a certain type to happen, you also need other flows to happen concurrently, and you can enforce these concurrency constraints mathematically. And the beauty of this formulation is that it looks complex, but it's actually quite elegant and simple to implement. These three matrices, A, B, and C, essentially capture the whole problem. The mass balance, the flow transformation, and also then the flow concurrency. And of course, you can have multiple choices of propulsion, multiple trajectories, trade-offs between delta V and time of flight. So we essentially applied this to a Mars exploration scenario with the same demands or conditions as the current official way to get to Mars with humans, which is DRA 5.0, the Design Reference Architecture 5.0. And we got this response here. This is for minimizing the injected mass in low Earth orbit. So we want to minimize what we launch from Earth. That's our main objective function. And this is essentially the solution we got. I'm going to explore this in some more detail. And then we subject this to a sensitivity analysis with respect to the productivity of the in situ resource utilization technology. And the key result here was 68% mass savings And when we first got this result, I was incredulous. We were really surprised by this, and we've looked at it in great detail and confirmed that this is indeed the case under the assumptions that were made. So this is essentially what the solution is. The solution is you first deploy a in situ resource utilization system, very consistent with what Dr. Spudis was telling us earlier. And you do this both on Mars, for example here, Gale Crater as a potential location. Mars ISRU is very interesting because you can do both atmospheric harvesting. MIT is currently developing an experiment called MOXIE that will use solid oxide electrolysis on Mars on the 2020 rover to demonstrate this for atmospheric harvesting, but you can of course do lunar or Mars soil processing as well. You do the same on the moon. You produce these resources, particularly liquid oxygen and hydrogen, and you then transport those, in this case, to an Earth-Moon Lagrange point 2 depot. And on the outbound trip, the crew, in fact, passes through the Earth-Moon L2 point, refuels the spacecraft, and does the trans-Mars injection burn from Earth-Moon L2. On the return, then, the crew comes back directly to Earth and takes advantage, of course, of air capture on the return. Now, how sensitive is this solution to the performance level of the ISRU technology? So our baseline assumption is shown here. This is a metric that we call ISRU resource production rate. It's expressed in kilograms per year per kilogram of plant mass. So a number of 10 essentially means that an ISRU plant can produce 10 times its own mass in resources per Earth year. That's what this factor of 10 means. That is perhaps quite aggressive. So as the capability of the technology degrades, towards zero, you can see this zigzag-shaped curve. The red curve shows you the Mars ISRU, and you can see that even at a level of 0.5, the Mars ISRU already starts paying off very early. So if you're going to use ISRU in conjunction with a Mars campaign, you would first do it at Mars. But then the moon kicks in at about 1.8 and really becomes significant at a level of 3.5. The reason this curve is has such a zigzag shape is because as you hit certain technology capability levels, the optimal topology of the network changes, taking into account the capability level of the technology. So through this approach, we can really look at how the optimal supply chain approach changes as technologies mature and hit certain threshold levels in terms of capability. On the moon, for example, one of the techniques, of course, water ice is the best. There's no question about this. But you can also do molten regolith electrolysis. We did some detailed studies on this. Essentially, you melt the regolith, which is different types of metal oxides, iron oxide, silicon oxide, or aluminum oxides. And you need a lot of energy to do this. But you can do it, and it's been proven on Earth that we can do this. The question is, can we create a package and a plant that is effective and reliable? What's interesting is to scale this in situ resource utilization MRE plant from a small scale pilot plant to a larger production plant. And you can see this in this curve as we scale up the annual oxygen production level. Our productivity measure that we talked about, this is the kilograms of resource per kilogram per year, starts increasing. This is well known in chemical processing, economies of scale. And then we asymptote, in this case, at a level of about 7. So the baseline assumption we had was 10, here about 7. We are in the right ballpark with these assumptions. Okay, and this is what physically this would look like on the moon. In this case, we use photovoltaics to power this. You can also use solar concentrators quite nicely. Finally, what's the payoff, and how do you deploy the ISRU infrastructure in the first place? So it turns out that when you again optimize this, that nuclear thermal rockets are very attractive. Nuclear thermal rockets have an ISP of about 900. And in many of the cases that we've run, we find that nuclear thermal rockets are excellent as a propulsion technology of first frontier. Before you have ISRU in place, nuclear thermal rockets are very, very effective. Once the ISRU is deployed and you have this fuel economy going, then the chemical propulsion can take over from the nuclear thermal rockets. Of course, a solar electric propulsion could also be interesting. We haven't looked at that yet, but that's easily included in the framework. The bottom line here is that you do need to invest in the in-situ resource utilization infrastructure, but already with the second Mars mission, DRA 5.0 style Mars mission, you achieve on a per mission basis a 68% savings, and so the crossover occurs already with the second mission in terms of injected mass in low Earth orbit. And so we're very excited about this. We had a meeting at NASA headquarters with the chief technologist and the chief scientist of NASA about 3 weeks ago to discuss these results with the NASA ISRU community, and it's a very active debate at this point. So to finish here, summary of my key points. It's time for a network-based approach. Let's move beyond one mission at a time. Even let's move beyond campaigns. Pioneering space, certainly with humans, will rely on a combination of traditional technologies, new technologies such as in-situ resource utilization, in-situ fabrication and repair, and advanced ECLIS. And we do see a role for nuclear thermal rockets, particularly as a propulsion technology of first frontier. Lunar plus Mars ISRU have the potential to save up to 68% of injected mass in low Earth orbit relative to a DRO 5.0 mission. And a lot more research and development is clearly needed on the ISRU technologies, solar electric propulsion. What happens if the launch costs, the way Dr. Elvis was talking about, drop dramatically? This will definitely potentially shift the attractiveness of these technologies. And we do need technology demonstrators to prove that the resource is there and that it can be produced. And my last point here is we do need to also clarify the current international legal frameworks to be allowed to actually do this. And there's no question about this. And then finally, this is a picture. This was our on the MIT homepage back in October. This has been known to the community as the lunar layover strategy. So let's do a layover at the moon on the way to Mars. And thanks for your attention. I'm happy to take a couple questions.
Thank you, Olivier. Thank you for keeping to time. So we do have time for questions. Well, I can wait for the microphone because it's being recorded.
You touched on this a bit in your last slide. So you optimize the system by trying to find the lowest mass to get to Mars. But does your system also account for costs? Because the cost of a factory that goes to Mars is obviously a lot higher than just launching a big fuel tank.
That's right. So we did not, in this study, we did not do cost modeling in terms of development cost, launch cost, and so forth. That's definitely needed. And clearly developing the ISRU plants, you need a lot of technologies to pull this off. You need clearly the resource harvesting, the ISRU. You need cryogenic fuel storage. You need automated shuttles, that transfer the fuel. You need to do station keeping with fuel depots that have fuel slosh, and there's a lot of technologies that need to develop that will not be cheap. And I imagine that if you do the financial analysis, you will also have a crossover point, but it might be further to the right than after the second mission. But again, the question here is, are we in it for the long term, or is this short-term thinking? Please.
Thank you. Tremendously impressive and exciting. The key word that leaps out is topology. And the phrase it brings to mind is optimizing the salesman's travels. May I make a suggestion?
Yeah.
Because even lunar water is non-renewable, whereas cometry and other water sources can be treated as meta-inexhaustible, The suggestion is using solar energy and the combined rotational and orbital angular momentum of the moon to launch from the far side using solar-powered post-Lathwaite linear electric motors wherever possible.
Well, thank you very much. Thanks. I agree about your comment. It's all about topology. I agree with that. Comets, they're very interesting. Of course, the big challenge with them is they come by so infrequently. So there's a time synchronization issue that you'd have to deal with, but I like your suggestions.
With the resource vector, did you model maintenance as an overhead of these factories and spacecraft?
Great question. So this number here, this whatever this productivity number here is, does need to include. It's an all-in number. So it includes the equipment for harvesting the regolith, filtering it. In this case, the power system. And if you have redundancy either or spares, robotic maintenance. Now, we're envisioning these ISOU plants as being not human-tended. So there needs to be some self-repair capability. And this mass number is all in, including the spares. But it's a great point. And what we do account, though, is a degradation in performance over time. Like a lot of chemical plants, they work great, especially batch-based systems. They work great, the first few batches, and then every batch after that, you have some degradation in performance. We do take into account degradation over time.
One more quick question? No? Okay. We thank Olivier again for a very
Thank you.
interesting talk.
I have copies.